And you can guess, right, that these guys would be important? Things that I've underlined?
You're on now.
I'm on now? Okay, so for those of you far away, we had battery problems, but we're powered up. So the question is, since it's unrealistic to know the entire distribution of sales, say, that would be quite a lot of information. We want to come up with some hack and replace BK with some other statistics based on the observations. We really want to use what we observe to use. We're observing the YKs, and we want to take certain features out of our observations and come with a feedback law based on those features. All right. So I'm underlining these because it's obviously what you care about. I mean, I want to maximize this expectation. So therefore I want to see which of these guys is bigger. And you can imagine something like this. Then you can imagine, just look at the mean. We have estimates of the average reward. So let's replace that t by an n. So my estimate of the mean is just this sum divided by the total number of times I've looked at it. Oh, and that's not xk, right? I'm not observing xk. I'm observing a noisy version of xk, so I've got to undo what I took away. I've got to replace this by something observed. Yeah. Yeah, because that's observed. I can observe yk. I can't observe xk.
There's no y. There's no I anymore, right?
Oh yeah. Thank you very, very, very much. Yep. That's right. And so what you find is that it is true that this will converge as n goes to infinity to the expectation of if uk equals I, then yk is just xi plus noise. So it'll converge to the expectation of xi. So it will work. I mean, that you can prove. But under what conditions, everybody?
Statistically independent.
No, we did all that. No, all the assumptions already made.
Large numbers.
Now, what do you need? What do you think? Look at this. Look at this division.
Oh.
That better not be 0, for example. Yeah. So this thing here, it's given a name in the literature. It's called Ti. Well, I'll put a superscript. Yeah. Well, I mean, whatever. There's no standard language for this, but yeah, you need that to go to infinity. So we're gonna use this thing about the number of times we pulled the ith arm, and we need that to go to infinity. All right. So in order to learn, we're gonna have to pull. If we learn exactly, we'll have to pull each arm infinitely often. Yeah.
So the goal is that we want to find the distribution of...
No. Forget, we do not want that. The only goal is right there. So our only goal is to maximize overall inputs this expectation. And t maybe is large. That's the only goal. And so the program would be is to say, well, the dynamics are so trivial and the observations so trivial, you can write down, this is a completely trivial, you could write this down in a second, very, very simple formula for this filter. The only problem is we don't know how to initialize it.
To initialize the B0 here is...
We can't, it's impossible. Knowing B0 would mean you could just find the mean. And if you know the mean, you know the policy. You just pick the arm with the biggest mean reward, you're done, Yeah, that's it. So,
but doesn't the variance come into play as well?
Not for this. It's a mean. You're thinking about something else.
I
And
was thinking, like, say the arms means are pretty close
Doesn't-
together,
yeah,
but then
no.
the variance of one.
it'll
variance-
come, variance will come up in a moment, but not here. The optimal policy is right there. Because it's just a mean. There's nothing. There's no risk sense. There's no risk aversion.
This costs.
Yeah. So that's this. Won't look at this problem. Yeah. There are many problems where variance is important, but variance is important in learning. Clearly. Yeah. I mean, definitely that will come up. You'll see in just a moment. But not for this. It's completely. I mean, given this thing here, it's. Yeah. I mean. You see, I mean, we're looking at just, I remember x0 is independent of the noise. You know, if I, yeah. Now this is the optimal strategy. If you want a proof of that, I'm not going to do, I didn't even think that somebody'd ask for a proof. I'll give you one, it'll take a second, but I'm not going to do it now. I know the risk of that. But it's very, very, no, variance is not an issue. That's the optimal policy. Okay, so what are we going to do now?
When you code this up, I mean, can we just do like equiprobable for B0? Like say each state's equiprobable?
Oh no, but, well that's a really good point, everybody. So one thing you could really hope is that I could just stick in some hack for B0. That's not right, you know, and run this, you know. And the problem is that there's no stability theory for nonlinear filters, you know. It's very fragile. Now, I conjecture that, in fact, I know that under this assumption, it would be stable, you know. That, you know, you pull each arm infinitely often, that you'll forget the initial distribution, so B0 won't be relevant. But then you come to complexity, you know. I've got, you know, I mean, if there's a large number of x's or something, it's very complex to run this filter. And as we'll see, there's no reason anyway. The hacks work, you know. But that's a good point. So if the filter was more, if we knew the filter had really nice stability properties, suppose it forgot its initial distribution exponentially fast, regardless of the input, then we could just stick in some stupid hack and be done with it. It's pretty easy to see that if you don't pull an arm, you don't learn. So if I never, ever, ever pull an arm, I never observe that x, and so my B doesn't change. So my BM never changes unless I pull the corresponding arm. So yeah, so that's a whole topic in itself.
But I mean, is that fine to just initialize B0?
No.
I mean, so you're saying there's no stability theory for it.
That won't work.
But then would you go back and just rechange B0
It wouldn't work.
Get it to converge?
I don't know. That's a research topic. I don't know. Nobody's done that. Nobody's done that, and I don't know how to make it work.
Okay.
Okay. Yeah. No. I mean, but it's an important point that the stability of the filter is what screws us up here. You know, we don't. And it's just not true. Yeah. I mean, it's not universally it doesn't have some universal stability guarantees. It all depends on the input. You know, and. So yeah, so it's not done. So what do people actually do? I mean, before I get into the hacks, these will be important parts of our hack. So that's going to be in our surrogate for the belief state. You know, but how do people actually say whether a policy is good or bad? I can kill this now. So it is going to be true. We're going to take our phi k, our uk, I mean, it's going to be some function which will depend on time, and it's going to depend on this guy. You know, basically think of this as a two-dimensional vector. You know, m hat 1 and m hat 2. And it's going to depend on all sorts of the junk, possibly. And then you have to say, well, how do I think about performance, because anything is going to make the average reward optimal. It's trivial to do that. You know, I mean, look at this. I mean, in the long run, this is a case where average reward is ridiculous, because I could just pull an arm lots of times, and I'm going to learn the optimal mean, and I know the policy, and so the average, almost any stupid algorithm will give you optimal average reward. What you want to do is preserve this sum and not average, not divide by t. And so the criteria for success so it's just equal to that. Minus what we started with. And this, of course, is what? Well, xk doesn't depend on k, and so it's just x0. So it's just, we're looking at the maximum mean. Okay. All right, xk is just equal to x0. I star is the optimizing I here. It's the I that maximizes this. And so this sum is really not a sum at all. It's just x0 with the best I times t, because there's t of them. And I got the max of m1 and m2. Because the mean of x0 I star is this maximum. It's the maximizer. If you like.
You're saying that's less than or equal?
No equal. No, no, no. All right, I'm comparing. So I claimed, I didn't prove it, I realized, but I will prove it, that this is the optimal policy if I knew the means.
That's true.
Okay. Yeah, okay, cool. And so when I apply that policy, I pull the same arm every time. I star, I star, I star, I star. That's what I'm saying over there. You know, yeah, I star is the optimal I. And so this thing here is just, let's get rid of it. 0. It's the same thing. Doesn't depend on k. Remember, the xk doesn't change. Remember, my dynamics have been erased, but xk plus 1 equals xk. there's no dynamics. It just is stuck. So that's why this, you know, take the sum outside, you get a t. You just get the mean of this, which is a maximizing mean. All right. So some facts. I mean, under almost completely trivial conditions, this goes to infinity. And I'll call it Rn, say. I mean, this requires conditions, you know, but, you know, I mean, it may be degenerate. It may be the noise is 0 or something, but if the noise is not degenerate, then the regret goes to infinity. That's a t. Secondly, if it's a good policy, you can get as good as logarithmic. So that's when you can hear this term all the time. Hold on a second, in computer science. Logarithmic regret. logarithmic regret, logarithmic regret. You hear it over and over and over again. They're referring to bandit problems, and there's generalizations. So the regret goes to infinity, but very slowly, because log is like nothing. Yeah, so what?
Just to clarify,
Yeah.
it goes to infinity as t goes to infinity.
Oh, yeah. Yep. But the growth rate, if it's a good policy, and the best you can do is this, under general conditions. And 3, you can even optimize K. So the optimal bound has been known since the 80s, and it's beautiful stuff. Make you bring tears to your eyes. That's really cool stuff. But beyond the scope of this course, it's beyond the scope of this course. I can kill this now, right? Can I? I guess I'll keep that first line. It comes back to your question about variance here. This is where the variance comes in. And it's not quite variance. Let's see, so, yeah. Yeah, what's possible that, say, M1 is much, much bigger than M2, Say M1 equals M2 plus 10 to the 10th, I don't know. 10 to the 100th, I just put 100 in. But the distributions are really close together. I'll make it like that, 10 to the minus 100, where that's the relative entropy. You don't know what that is, I don't care, I won't define it. But mu1 is the distribution of the observations, really. So mu1, so it's really the noise that's going to be important here. Oh, that's right. These are separate topics. Yeah. That's the thing, is that I've deviated slightly from the standard Bandits problem by making this Bayesian, by making the initial distribution Bayesian. So what I'm saying here, there's a bit of tension here between most people don't bother with a distribution in X0 at all. They make this deterministic. That's why I made a mistake at the beginning of the lecture. That's the non-Bayesian setting. The Bayesian setting is you make this random. And that doesn't make such a big deal. But where things can get screwed up is that you have, oh damn, that's confusing. No, this is bad then. So I'm going to change way to throw it down. I have to write it this way. Sorry about that. I've got to shift the mean. So this is zero mean. So even though the means are very, very different, so even though M1 and M2 differ by 10 to the 100, all right, and even though the W's have zero mean, so you'd think, wow, that's a big difference because you're adding a very different constant. I can easily give you an example where this is true. It's really easy to do that. I just basically take distributions which almost don't have means, something with a really heavy tail, and then truncate it. And I can make the means differ wildly and yet make the relative entropies very small. So relative entropy is, well, take the log-likelihood ratio between the two distributions and integrate it with respect to mu. That's the Keil divergence. Now, it turns out that's what makes it hard or easy to do. So this constant K star is a function of its relative entropy. I think it's 85. I got it down here for myself. So I mentioned, does anybody remember I mentioned lie? Yep, 85. Two heroes, insane heroes. You know, Lai is the most amazing person and scientist on Earth, and I guess Robbins is too. And two of my favorite topics, you know, were launched by Robbins. I mean, one is Bandits, and the other is Stochastic approximation. So we were supposed to have Lai visit in 2 weeks. He's a professor at Stanford, and it's canceled.
Today, you must have visited.
Oh, today? No, I thought it was in 2 weeks.
Yeah.
March to that. I mean, you said the.
Oh, fuck, that's right. Yeah, it was supposed to be today. Yeah, not 2 weeks today. And it was canceled. So Lai's not coming. He'll probably come in the fall. But he's a beautiful speaker, you know, even though he does technical stuff. Just amazing person. So anyway. So yeah, I saw this first as a grad student. Couldn't believe it, how pretty it is. But it's too much for this. Now, back to hacks. So, tell me, everybody, what would you do? Tell me, what's a policy? So, I'm going to show you that you can get rid of the junk. This will work. Forget the thing. You can just take these stupid estimates of the mean, and that's enough. And if a really naive audience, they tell me exactly what the policy is. I lost this one. We're going to red. So if I told you that I'm going to take UK equals some function phi k of this estimate there, you know, and I also told you I want to maximize this. I want to maximize. I mean, look at this. I mean, ignoring the division here, this is so closely related to my objective. You know, then almost anybody. I know you guys won't do it because you don't want, you're scared of being tricked. But almost everybody would say, well, geez, take the empirical max. I mean, I know what the optimal policy is. You know, again, U star k equals the arg max yeah. It's just the arg max of the means. And there's my estimates of the means, which are consistent. They converge. You know? And so I want to maximize the reward. I'm going to do it, right? That's what, so this is like the first thing people would try. I mean, that's a policy. What do you think?
I think it has issues.
Yeah, yeah, go for it.
I think the first issue is, you know, until we get enough data, we're not going to be confident that we've explored enough, and that's one thing. But another thing is, we need to convert to some steady state distribution.
No, there's nothing about steady state here.
There has to be
Nobody cares about steady state. No, 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 no. We're talking about no, no, no. The real question is about a finite time horizon. No, no, there's no steady state. Nobody gives a shit about steady state. You know, 'cause it's a meaningless thing. In steady state, I can make this basically just go back and forth. First arm, second arm, first arm, second arm.
Bang, bang, bang.
Well, yeah, but why not? Just half the time I go to one, half the time I go to the other, any way you want. And I know that in steady state, I'll get the exact means, I got the upper policy, big deal. I mean, that's not what people care about. Remember, that's why I mentioned this thing about regret. I mean, you know, you want to learn fast. So having logarithmic regret means you're learning fast, and I'm actually giving the advertising company what they want before the world is over, you know. So forget that. So that, the first thing you said is right, is that why on earth would you have so much, you know, be so naive, you know? I mean, it's just that, you know, here's an example of what happens, right? You get that, suppose that, you know, M1 equals 1 and M2 is equal to, you know, 10. And actually, yeah, I wish I had 2 colored pens. Actually, I've got my relative. I'm going to keep this. I need this somewhere. You know, let's my mui's that I used here to define this relative entropy. Let's just use this to help us think. And so it goes back to your variance question or point. Damn. So I've got, and I'm going to look at this case where mu2 is 10, m1 is 1. So, and I might look at, maybe it's really nice, this 10. And that's you know, I'm saying there's a density. That's the density for mu1, mu2. All right. Now, so that's the better one. I'm getting a reward of 10 versus 1. That's the guy I want to pick. But what can happen is you've got M2 over here, M1 over here. And it might just be really heavy tail, or really have a very high variance, as was astutely pointed out. Yeah. All right. Okay. So, so it's possible is that at time. So I pull arm 2. I'm lucky the first go. So suppose, let's just do an experiment. Here's a simulation. So U0 equals 2, which is equal to I star. You know, I just got lucky the first pull, but I got unlucky because I ended up getting a value of y1 equals 9. So it's a simulation. I drew this random variable here. This is fixed, and I happen to get 9. Okay, and then and actually, oh damn, I'm going back and forth between Bayesian and non-Bayesian. I'm sorry. That's the problem with trying to prepare a lecture when you're sneezing constantly. I forgot to say that there's some subtleties here. So in order to apply this sort of, so basically as soon as you see this trap with the nonlinear filter, you say, forget Bayes, although people don't always forget Bayes. Let's just think of this as just a deterministic quantity, you know, and then this is the distribution I care about, you know. So that therefore, you know, this is valid now. Think of that as deterministic. That's random because it doesn't change. That's the point. But with this rule, of course, you can't. You have to at least try out the other guy once. So the next thing I say, well, that's pretty good, 9, but just I'm going to. There's nothing to do in argmax over. So this is just a random choice. I'll have to go through and try u 0 equals 1. And I don't know, 55. It's not possible, you know. Say this is Gaussian. This guy, you know, there's just some huge sale, you know. typically, you know, the New York Times people just buy the sock, but somebody came in and they bought 100 cashmere sweaters and a Rolex watch. All right, so you go, ooh, and so now you've got your means, right? So now we've got our m hat 1 equals 9, because there's only one pole, or 2. And that's M1. Our mean at time 1 is 9, and our mean of 1 at time 2, because I'm looking at the second observation, is equal to 55. And you go, holy shit! I hit the jackpot. So under this policy now, you would then draw I'm sorry, U1. Sorry, this is at time 0 I drew 2, and I'm going to the next time point I'm drawing 1, which made my next observation equal to that. And so now I'm going to take the argmax, use this policy, definitely U2 will be equal to 1 again. And I'm going to get my observation, and maybe it's not going to be so stupid now. Maybe it'll be more in the middle here. So maybe it'll be actually closer to 1. Maybe it'll be 2. Maybe I'll get lucky again. I'm just saying it's a possibility. You could do a simulation like this. And so basically what's going to happen is, oh, I shouldn't have said 9. No, I can't be that. I have to be more unlucky than that. I fucked up. Excuse me.
I mean, it's likely.
No, it's like, but it's because of my simulation. It's so this does not have bound. So if these had bounded support, the problem would be trivial. It's got to leak over. It's got to have support over to the left. It's got to be possible to be worse. So instead of that, I'm going to take it to be a half. All right, it's just an example. Now the point is now that that's below the mean. So M1 is 1. I have to, for this example to work, I have to end up getting a draw from this guy, which is below the mean of the other one. And so my point is that, so this is not 9 anymore, it's a half. And so U2 is going to be 1, U3 is going to be 1. So basically what's going to happen is that UK is going to be equal to 1 over and over and over again, because this 1/2 is absurdly small. And so what's going to happen is UK is 1 forever. I'll put 3 bars there, which means that my estimate of 1 is approximately equal to the mean value, M1, which is bigger than, by lots, than a half. You know? And since my policy is to take the maximum, And this is approximately equal to the consistent value. I'm just pulling one. I'm saying, oh, 1 is better than half, 1 is better than half, 1 is better than half. I get convergence of this to M1. I also get convergence of the other guy. This thing's going to converge. It's going to actually converge to 2.5. It'll be equal to half all the time. Because since we never pull it. So this is something that could happen with positive probability. I get one bad draw, just one bad draw from the good guy once, and then it makes me pessimistic about this guy forever. Because I just keep on pulling this, I never learn a thing. So it's just expanding on what you just said. This issue of exploration is another thing that's chanted and chanted and chanted, and this is the example that people always raise. So this will never, nobody would ever do this. Right? Now, what do they do? So you need to explore. So for some of these people love to say this word. It's just a, that's exploration. Definition, exploration. I pulled the arm an infinite number of times. It's just, but how? So there's randomized rules. So in some contexts, maybe not this one, it's a reasonable thing to do. I can take, instead of a deterministic guy, I can take the probability that UK equals 1, say, is equal to, usually I put in an exponential. The exponential of m hat k1 divided by the exponential, of the sum of the exponentials.